Multi-fuel-based 6-stroke internal combustion engine. Abstract 6-stroke engine. The name itself indicates a cycle of 6 strokes out of which 2 are useful power strokes. According to its mechanical design, the 6-stroke engine with external and internal combustion and double flow is similar to the actual internal reciprocating combustion engine. However, it differentiates itself entirely, due to its thermodynamic cycle and a modified cylinder head with 2 supplementary chambers, combustion and an air heating chamber, both independent from the cylinder. In this, the cylinder and the combustion chamber are separated, which gives more freedom for design analysis. Several advantages result from this, one very important being the increase in thermal efficiency. The 6-stroke is thermodynamically more efficient because the change in volume of the power stroke is greater than the intake stroke and the compression stroke. The main advantages of 6-stroke engine includes reduction in fuel consumption by 40%, 2 power strokes in the 6-stroke cycle, dramatic reduction in pollution, adaptability to multi-fuel operation. 6-stroke engines adoption by the automobile industry would have a tremendous impact on the environment and world economy. Introduction to 6-stroke IC engine. The 6-stroke IC engine is advancement over the existing 4-stroke IC engine, which employs the same principle as that of the 4-stroke IC engine. The 5th stroke or the second power stroke uses the heat evolved in the exhaust stroke, directly or indirectly, as heat required for the sudden expansion of the secondary fuel, air or water, which pushes the piston downward for the second power stroke, thereby rotating the crankshaft for another half cycle. As heat evolved in the 4th stroke is not wasted, the requirement for a cooling system is eliminated. Here fuel is injected once in every 3 complete cycles of the crankshaft, which is any time better than a 4-stroke IC engine where fuel is injected once in 2 complete cycles of the crankshaft. It should be noted that efficiency of the 6-stroke IC engine is more than the existing 4-stroke IC engine. 2 major types of secondary fuels used in the 5th stroke are air and water. Many types of 6IC engine have now been designed on these 2 fuels, of which few important types will be discussed. Types of 6-stroke engines. 1 Crower 6-stroke engine. 2 Bearhead 6-stroke engine. 3 Bajulaz 6-stroke engine. No cooling system required. Improves a typical engine's fuel consumption. Requires a supply of distilled water to act as the medium for the second power stroke. 1 Crower 6-stroke engine. In a 6-stroke engine patented in the US by Bruce Crower, after the exhaust stroke, fresh water is injected into the cylinder, and is quickly turned to superheated steam, which causes the water to expand to 1,600 times its volume and forces the piston down for an additional stroke. This design also claims to reduce fuel consumption by 40%. Crower's 6-stroke engine features. 2 Bearhead 6-stroke engine. Ducati SL500 motor with Bear 6-stroke heads. Figure 1, Bearhead 6-stroke engine. This engine simply replaces the conventional 4-stroke engine cylinder head. The manufacturer's 4-stroke bottom end remains unchanged. The engine utilizes an overhead short-stroke crankshaft and piston arrangement which opens and closes inlet and exhaust ports leading through the upper cylinder liner. The Bearhead technology can be fitted to new production engines or retrofitted via aftermarket replacement. The top and bottom crankshaft are connected via a drive chain or toothed belt. The top crankshaft and piston become positive power contributors to the overall power output, thus increasing the amount of power/torque generated by up to a possible 35%. In essence, the engine results in having 2 pistons operating and producing power within each cylinder. The absence of valves, springs, retainers, and guides mean that the engine's bottom end has been freed up from laboring and is allowed to spin up, producing more power. The additional torque and power further generated by the top piston/crank of the cylinder head is then channeled via the connecting drive chain to the bottom crank. The net result of the engine is tractor-type pulling torque never before realized from a 4-stroke internal engine. The sort of steady locomotive-type performance gained can only be likened to steam locomotives or diesel engines. The net result is power/torque increases of 35%, conservative. Simpler and less expensive manufacturing and tooling. Reduction of cylinder head reciprocating parts. Lower maintenance costs due to less wearing parts, cylinder head. Longer cervic engine intervals possible due to lower operating temperatures recorded. Increased economy due to the ability to operate and produce full operating power of much higher air-to-fuel ratios. Reduction of exhaust emissions due to less fuel being consumed and the real prospect of meeting Euro 4 emissions standards, doing away with the catalytic converter. Possible one-piece engine block and head casting, saving more manufacturing costs. Usable torque at as low as idle means suitability for lower RPM operation and adaptation to CVT, constantly variable transmission. 3. Bajulaz 6-stroke engine. The Bajulaz 6-stroke engine is similar to a regular combustion engine in design. But however there are some modifications to the cylinder head, with 2 supplementary fixed capacity chambers, a combustion chamber and an air preheating chamber above each cylinder. Motor. Figure 2, Bajulaz 6-stroke engine. The combustion chamber receives a charge of heated air from the cylinder and the injection of fuel begins an isochoric burn which has increased thermal efficiency compared to a burn in the cylinder. The high pressure achieved is then released into the cylinder to work the power stroke. Meanwhile a second chamber which blankets the combustion chamber has had its air contents heated to a high degree by heat passing through the walls from the burn. This heated and pressurized air is then used to power another stroke of the piston in the cylinder. The advantages of the engine include reduction in fuel consumption by at least 40%, 2 expansion strokes, work, in 6 strokes, multi-fuel usage capability, and a dramatic reduction in pollution. Bajulaz 6-stroke engine features. Reduction in fuel consumption by at least 40%. 2 expansions, work, in 6 strokes. Multi-fuel. Dramatic reduction in pollution. Liquefied petroleum gas. Costs comparable to those of a 4-stroke engine. Bajulaz 6-stroke engine. Design and construction. The engine consists of 4 valves, intake valve, 1, heating chamber valve, 2, combustion chamber valve, 3, and the exhaust valve, 4, which control the flow of the fluids in the cycle. Engine consists of a combustion chamber for burning of fuel-air mixture, 6, which is completely isolated from the cylinder and the burning of the fuel has no direct effect on the piston as in the case of a 4-stroke IC engine. An air heating chamber surrounds the combustion chamber which holds pure air under high pressure. Heat passes from the combustion chamber to the air heating chamber. The wall of the combustion chamber allows transfer of heat to the air heating chamber which heats the air under high pressure which is eventually used in the 5th stroke. The burning of the fuel does not have any direct influence on the piston. The energy released by the combustion passes through valve which enters the cylinder and hence work is done on the piston. Working. The working of the 6-stroke IC engine is very similar to the 4-stroke IC engine. The first 4 strokes remain the same with the addition of 2 more strokes discussed below. 1. Intake valve, 2. Heating chamber valve, 3. Combustion chamber valve, 4. Exhaust valve, 5. Cylinder, 6. Combustion chamber, 7. Air heating chamber, 8. Wall of combustion chamber, 9. Fuel injector, 10. Heating plug, 11. Piston, 12. Crankshaft. First stroke, the inlet valve, 1, is kept open. Due to cranking, the piston moves downward which results in the formation of a pressure difference due to which pure air enters the cylinder, 5. The crankshaft rotates for half cycle. Second stroke, the inlet valve closes and the heating chamber valve, 2, opens. The piston moves upwards due to cranking forcing the pure air into heating chamber, 7. The air at this stage is converted to high pressure. The fuel is injected in the combustion chamber and the fuel is ignited as shown the figure. Initially compressed air is present in the combustion chamber which results in the formation of fuel-air mixture. Part of the heat evolved will pass through the wall of the combustion chamber, 8, and it heats up the compressed air present in the air heating chamber. The crankshaft completes another half-cycle rotation in the second stroke. At the end of 2 strokes the crankshaft will complete 1 cycle. 2 temp. Third stroke, first power stroke, the combustion chamber valve, 3, opens and the gases of combustion enter the cylinder, 5. This pushes the piston downward and hence is known as the power stroke. The crankshaft rotates for a half cycle. It should be noted that the air in the heating chamber is continuously heated and this results in further increase of pressure. 3 temp. Fourth stroke, exhaust stroke, the exhaust valve, 4, opens. The piston moves upwards and the exhaust gases are removed via this valve. The crankshaft rotates another half cycle. At this stage the crankshaft completes 2 full cycles. In this stroke, less amount of heat energy is expelled out when compared to the 4-stroke IC engine, as this heat has already been used to heat the air at high pressure in the air heating chamber. 7. 4 temp. Fifth stroke, second power stroke, the heating chamber valve opens and the pure air now at high pressure and high temperature enters the cylinder as shown in the figure, which does work on the piston and hence it moves downwards, resulting in the second power stroke. The crankshaft completes another half cycle. 5 temp. Sixth stroke, finally the combustion chamber valve, 3, opens, the piston moves upwards forcing the pure air into the combustion chamber, which will be used as air for the fuel-air mixture in the third stroke or the first power stroke. The crankshaft will complete 3 full cycles at the end of the sixth stroke. Hence fuel is injected once every in 3 cycles of the crankshaft, whereas in a 4-stroke IC engine fuel is injected once in every 2 cycles. 6 temp. Cycle of 6-stroke engine. Graphical representation. Following is the graphical representation of the 6 strokes in a cycle. The crankshaft rotates a total of 1080 in one complete cycle. The 6 strokes are divided into 8 events, which are in turn classified into 2 categories, i.e. 1 static event, event occurs without the movement of piston. 2 dynamic event, event which occurs with the movement of piston. Otto cycle. Dual cycle. The heat that is evacuated during the cooling of a conventional engine's cylinder head is recovered in the 6-stroke engine by the air heating chamber surrounding the combustion chamber. As a result of this, less heat is wasted, which increases the thermal efficiency. After intake, air is compressed in the heating chamber and heated through 720 of crankshaft angle, 360 of which enclosed chamber, external combustion. The transfer of heat from the very thin walls of the combustion chamber to the air heating chambers lowers the temperature and pressure of the gases on expansion and exhaust, internal combustion. Better combustion and expansion of gases that take place over 540 of crankshaft rotation, 360 degrees of which is enclosed combustion chamber, and 180 degrees for expansion. The glowing combustion chamber allows the optimal burning of any fuel and calculates the residues. Better filling of the cylinder on the intake due to the lower temperature of the cylinder walls and the piston head. Elimination of the exhaust gases crossing with fresh air on intake. In the 6-stroke engine, intake takes place on the first stroke and exhaust on the 4th stroke. Large reduction in cooling power. The water pump and fan outputs are reduced. Possibility to suppress the water cooler. Less inertia due to the lightness of the moving parts. Friction losses, theoretically higher in the 6-stroke engine, are balanced by a better distribution of pressure on the moving parts due to the work being spread over 2 strokes and the elimination of the direct combustion. Electrolysis. Graph 1, graphical representation of 6-stroke engine. Comparison of 6-stroke engine and 4-stroke engine. Graph 2, Otto cycle. It is clear from the first graph that the work done by the 6-stroke engine is greater than the 4-stroke engine. Graph 2 is in reference with a petrol engine. Graph 3, dual cycle. Graph 3 refers to a diesel engine. The work done by 6-stroke engine is greater than a 4-stroke engine for the same amount of fuel used. Factors contributing to increased thermal efficiency, reduced fuel consumption and pollutant emission. Modifications made. The main commercial advantages of hydrogen production by electrolysis are its scalability and the emission-free production of hydrogen, when produced via renewable energy. Conventional electrolysis is the most common method used to produce renewable hydrogen. Electrolysis involves the separation of water into hydrogen and oxygen, using an electric current. Although some electrolyses use chemicals or intense heat to help the separation, conventional electrolysis uses no chemicals, and works at room temperature. Electrolysis separates water into its constituent elements hydrogen and oxygen by charging water with an electrical current. The charge, coming from two poles in the water, breaks the chemical bond between the hydrogen and oxygen and splits apart the atomic components, creating oppositely charged particles, see diagram. Because opposite charges attract, the negative pole, cathode, attracts the positive particle, with the hydrogen molecules, and the positive pole, anode, attracts the negative particle, with the oxygen molecules. As the particles reach the poles, the hydrogen and oxygen gases rise and are collected separately.